Yes, perfect. So, as we discussed earlier, yesterday we were talking about using the windows. So, when we talked about windowing a signal, so we had an idea of a rectangular window where all the samples were equally important. Then we said, hey, when we are taking a sequence of n, so the ends of that sequence is something which is causing the impulse and which is causing the phenomena of FFT leakage. So then we are not interested in the end parts of that window. So then we thought of tapering down the end parts of the window and smoothing it down. So we saw the concept of Hahn window. We saw the concept of Blackman-Harris window. So once I would like to show you again. So this is our yeah. So over here, let's take a case. So we will have a quick recap. And if we see the case where our input signal is actually lying on the bin, so then we have this rectangular window at exactly 129th bin over here. But the yeah, orange curve is something which is taking three bends. So that's the hand windowed signal. And when we talk about Blackman-Harris windowed signal, so it is taking more than three bins. So usually it takes about 7 to 9 bins, but it's not specific. It's just a layman term or layman number, but it takes more bins. So even though when the signal is lying on the bin itself, so over here, the main lobe of the windowed signal is greater. But then the thing is, even though the power is distributed in larger number of bins, but we saw a significant decrease in the FFT leakage when the F in by Fs condition is not satisfied, or let's say the signal is not exactly falling on the bin. So we saw this case where we said that, hey, let's look when the signal is not exactly falling on the bin. Then we saw that all the bins were occupied when we considered the rectangular window, and that was our main issue or main problem. So then when we went for hand window, even though the lobe was falling for three bins instead of one bin, but we saw a significant decrease in FFT. And when we go for Blackman-Harris windowed signal, so the FFT is even more significantly decreased, which is good for our case. Why? So then we looked the case. So where we are using the windowing technique. So while noise shaping or while we are working on delta sigma modulators or our analog to digital converters. So basically we have an input signal, and along with that we also have a noise. And when we plot the FFT of the same input, so we looked in yesterday's video. So we saw that at very low frequencies of the noise, uh, so over here, due to the higher attenuation provided by its high pass behavior, so even a little change will shift this noise from the bin. And due to this phenomena, the FFT leakage is being seen in this portion of this noise, and ideally this noise should go to zero at infinity, but it's not going to zero, but it is somewhere showing its FFT leakage and the bins are being occupied. So we will be confused or misleaded when we take the ratio of, let's say, signal to noise. So this is our input signal and this is our noise, which is high pass in nature. So then to come up with this problem, we said that if we windowed this part, let's say we are interested in the bandwidth, let's say BW, which is omega naught. So if we are like from 0 to 200, let's say, for example, or for instance, so between this bandwidth, if we window this signal, let's say using a Hahn window, so then we can see that the FFT is significantly reduced. And if the FFT is significantly reduced, then the accuracy of the signal to noise ratio becomes more precise. and helps us with obtaining the signal to noise ratio. So this is how windowing helps us. And why did we exactly used Han window? So we could have also used Blackman-Harris window, or there are several multiple options available for the windowing of the signal. But then we used Han window because the lobe, as we go for higher and higher precision, the lobe of the window itself increases, right? So in the case of Han window, the power is distributed over 3 bins, but in the case of Blackman Harris, it can go up to 17 bins or even more. So then, when the bandwidth over which we are interested is less, let's say for initial 30 bins, we are only interested. So if we are interested in initial 30 bins, then the noise at each bin will be spreaded for more bins. And when we go for when it is spread over more bins, then we cannot exactly consider all the noise lying over there, because it will exceed our bandwidth. And that's why over here we stuck up we stick to hand window. So this is how we use windowing technique for our good precision, and in this case for calculating signal to noise ratio. And then I would like to carry forward this series with new topic, which is quantization. So until now, we covered all the aspects of sampling. We talked about sampling, and we covered all the relative definitions and all the related topics regarding sampling. So now it's time to move ahead to the concept of quantization. So as we discussed in the very first video, we had signal in continuous time and continuous amplitude. So then we said, okay, let's first sample it down so that we have discretized it with respect to time. But still, even though at this stage we are able to do sampling, so we are able to discretize the continuous time signal into discrete time, but still we need to change convert our signal from continuous amplitude to discrete amplitude and assign a digital word to our signal. So then the concept of quantization comes into the picture, where we need to discretize the continuous amplitude to uh, let's say discrete amplitude. So now that we know everything about sampling, like for example, once the capacitor is charged with the sample, or it's being sampled, we can basically use an op amp to drive the other whole circuit without without disturbing the sample on the capacitor. So because that's what we are actually interested in, that's where our data lies. So we can basically use op amp. We'll look into that circuit, but as of now, uh, while quantization is considered, so as we can see this figure, so basically quantization is referred to stepping out the samples which we have gathered while sampling. So let's say for this example, we have a quantizer, or basically we are doing quantization with a 3-bit digital word. So basically we have from 0 to 7, we have 8 steps, and which basically means 2 to the power 3, um, and this gives us a 3-bit digital word going from 000, 001, 010, 011 to basically 111. So based upon where our value lies, or where our sample voltage lies, we can assign the digital word to that particular sample, and that's how we discretize this amplitude. So let's say we have an input which is being sampled and held on a capacitor. Now we want to figure out in which of these levels the input lies in. So these are the levels, and basically if we say that width of each range, so this is the width. So it is basically, we have our Vref. So water signal we have, it will lie between 0 to vref. If it exceeds vref, then it is saturation region, and if it goes below zero, basically it can't go below zero, but even after calibrating. So we are interested in like range till vref. So the width range is, let's say for a ideal quantizer, this is the ideal case where all the widths are same. So the width range can be given by vref divided by number of levels. So here we have 8. So we have vref by at 8. So this is our step size. So over here in this example, we have seen a 3-bit quantizer, and this is the ideal 3-bit quantizer where, let's say, when we try to design this ideal quantizer, obviously when we try to implement it using our circuits, the non-ideality come in the form of errors. So either a non-linear error or a linear error. So it's impossible to build an ideal quantizer. But then let's look at what kind of errors we might face. So first error might be that this curve can shift to either left or right due to the offset voltage. So this is basically called as overloading the quantizer, or the quantizer is saturated, where we are only interested in Vref, but then it goes ahead of Vref or below of Vref. So this is the overload region, and this is the non-overload region which we are interested in. So this might happen due to the offset voltage. Then our step size may not be equal, which is basically Vref by 2 to the power n. In this case, 2 to the power 3, which is 8. So we had Vref by at 8. So when we like, obviously at this is at particular local instance, the slope is either 0 or infinity. But when we draw a line corresponding to this steps, then we if we say that as a slope, so then basically if the step size is not equal, then the slope of the staircase might increase or decrease, and this is due to the gain error, or basically called as gain error. So you can see over here the step size might increase or decrease. So if it is increasing, then the slope is um, decreasing. So and small gain errors can be always calibrated. So talking about the next error, all the step sizes are non-uniform. So basically not same or not equal. So we have the step size, and like we also called the step size at as least significant bit, which is LSB. We'll talk about it in some time. So when we look at this quantizer, so all the step sizes are non-uniform, and if we see that code 1 is wider than the ideal step size, whereas code 2 is smaller than the ideal step size, and we have our vref going from 0 to this point. So we can also have a missing code. So we will also talk about it in the next slide. So the important thing is that when we want to specify a quantizer, we need to provide its list of information with it for all the analog input voltages at which the code transition occurs. So when we are quantizing amplitude, so basically the code is being transitioned right from 1 to 2. Let's say this is the level for 1. So from this voltage to this voltage, it lies between 1, and after this voltage it transitions from 1 to 2. So we need to provide the information or the list of information for all the analog input voltages, which are basically our samples which are getting sampled on the capacitor. So that range it where we have so for all the analog input voltages at which the code will transition itself. So like from 1 to 2, 2 to 3. So for example, we need to provide the width of each code. So that's information we can provide while specifying a quantizer. But let's see the characteristics of a quantizer. which can be specified by the first one is all code of uh, transition, or basically all code voltages for all code transitions. So basically we can provide the widths of all the codes. So when we talk about providing the widths of all the codes, so what we are talking is, let's say this is a code which is let's say denoted by integer which is k. Let's not say first code, second code. Let's say it's a code k. So basically this is vk and this is vk plus 1. So it has been transitioned from k minus 1 to k, and at vk plus 1 it will transition to k plus 1. So it goes from vk to vk plus 1, and the width is basically given by vk plus 1 minus vk. So that's the width with respect to voltage, and the width is given in let's say millivolts or some volts. So the code widths are nominally called as the least significant bit, or LSB. So, and it makes sense to specify the deviation of the widths from nominal step size instead of providing all the widths, because in a quantizer, not all widths are uniform. So then it makes sense so that we decide a LSB, and then we specify the deviation of the widths from the nominal step size. So the width of code k basically given by vk plus 1 minus vk, um, and the deviation of the code k from the ideal step size would be the width minus whatever the difference is there between the width and the LSB, which is least significant bit. So it has a dimension of, as I talked earlier, of some volts or millivolts. So this is called the differential non-linearity, or DNL, at that code K. So DNL is specified at that particular code K only. So in order to compare uh, between two or more different ADCs or converters, even though they have same number of levels or partitions, the absolute value of input range may differ from converter to converter. So it does not make sense to talk about the absolute DNL of a code, but we can normalize that absolute DNL at code K with the least significant bit. So when we normalize DNL with respect to LSB, so then we get the deviation. So basically this is the width, and this is the deviation is basically the difference between the width and the LSB. We can normalize it with LSB, and we don't talk in terms of millivolts, but we talk in terms of number of LSBs of that converter. So this is the introduction to quantizer. So that's all for this video from my side. Thank you so much. So if you have any doubts in quantizer, do let me know.